Yeah, there it is. I hope that all of you can see my slide. Is it visible to you? Can you please confirm, one of you?
Yes, sir.
Yeah, so do this confirmation quickly, okay? Don't sit idle. Okay, so we have very little time with us. Okay, so there are a lot of things that we have to cover like this. So the next topic that I'm going to start is digital transmission. Okay, digital transmission. So let me do like this. Before I go over here, let me share something else with you. Let me pull out my whiteboard. Next week onwards, actually, I have got something else through which I can actually draw things by hand. And for now, let us use our this Teams inbuilt whiteboard. Oops. Again, oh, I need to do it again. Is it not visible? Why it is not opening up? Yeah, so whiteboard is coming. Yeah. Okay. Can you all see it? Can you see the whiteboard? Quickly, please confirm. Oh, again it closed. Display content. I don't know what is happening. So let me do one thing. Let me use my notepad. Okay. And let me share this notepad. Let us do it this way. Okay. Oops. Why this is closing? This whiteboard is creating problems. There is problem in display of whiteboard. So okay. Now, can you all see my notepad? Okay. Is it visible?
Yes, sir.
Okay. Now, so let us assume that we have two computers, right? So we have two computers which are plugged in together, okay, directly. So whether it is crossover cable or whatever it is, so some way, so two computers will have to talk to each other. Okay. So this is something that we'll have to enable. How can two computers connected through a wire talk to each other? How can it do it? So what you will do is, through the physical medium, you are going to send, one computer sends some signals which get converted into bits, and these bits are transmitted from one computer to another. So whether it gets converted into bits, or whether the signals are sent in the form of signals or not, so that basically depends on the type of communication that is in place. So whatever be it, okay, so just visualize that one computer is connected to another computer. Now the question is that how do we enable this communication to take place? So let us try to understand. Okay, so let us try to understand. So first of all, what you need to do is you need to encode the data, right, that comes from one computer. You need to encode it some way, and then it has to be transmitted over the medium. Then the other computer can receive it. Okay, so this encoding has to be done. So how you are going to do this encoding? So if we are talking about, see, when we are talking about data can be of two types: the analog data and the digital data. And in a previous class, we already spoke about the analog data, digital data, the different types, applications, etc. So now let us not spend too much of time on this. So if we are talking about, let us start with the digital data, right? Digital data can be sent between the two computers either in the form of digital signals or in the form of analog signals. And the same thing can happen for analog data as well. Analog data can be sent in the form of digital data, digital signals, or in the form of analog signals. So let us assume for now that we have digital data and we will be sending the information in the form of digital signals. So you see the data that comes from the computers, okay, the transmitting computer basically, it has to be encoded in certain way, and it has to be sent over the transmission medium, right? So this is one part, right? So you need to do some kind of a conversion. You need to do some kind of conversion, and that is called encoding. You need to do a certain kind of conversion, and that is called encoding. So if you are encoding at the sender end, you also need to decode at the receiver end. So ultimately what is going to happen is that in the sender end, at the sender end, you are going to have the digital data in the form of zeros and ones. So these zeros and ones will get encoded at the sender end in the form to give rise to digital signals. And you have already seen how the digital signals look like, with discrete signal voltage levels, with discrete voltage levels like plus V, minus V, that kind of thing. So these digital data will be encoded to form the digital signals, which will be sent over that link. The receiver basically is going to receive the signals, the digital signals, decode the signal, and it's going to get the transmitted digital data in the form of zeros and ones at it. So you see that this is what we need to understand, that how this digital data is going to be sent as digital signals. The same thing with some other mechanism can also be used to send the digital data in the form of analog signals. Instead of digital signal, you will be using analog signal. That is also possible. And that is something that we will talk about later. So first, let us try to try to focus on digital data being sent as digital signals, right? So so we'll focus on that. Achha. Now, so one is encoding. Basically, this kind of encoding has to be done. The digital data has to be converted into digital signals. The second thing that is very important when you have this kind of sender to receiver direct link between the sender to receiver, like computer to another computer connected together, right? So how you are going to do it? So one thing is that this encoding is important. This is understood. What are the other important things? Can you tell? Can you visualize what are the other important issues that will have to be taken care of?
Loss of data.
Loss of data. Very good. Loss of data. Right. So what are the different types of losses of data? So let me write loss of data. So what kind of loss we are talking about? What kind of losses?
Transmission losses, sort of.
No. So that is understood. But what kind? Can you specify a little bit? What kind of transmission loss? Loss means what? So let us say that some bits are transmitted, right? 1001110, like that, whatever, right? So whatever you are transmitting, not everything, due to the medium, nature of the medium, or whatever the physical characteristics of it, not everything basically arrives at the source correctly, right? Maybe some bit gets dropped, some bit gets corrupted. So the 1 basically changes to 0 in between, or 0 to 1, whatever. So you need to basically take care of this mechanism, and this is called error detection. Error detection, and along with error detection, you need to have, I hope that all of you can see my notepad. Along with error detection, you have error control. Okay. Now, now the other thing that is very important when you have a wire connecting two different computers, can you guess what it is? Another very important thing is also there, among many others. But apart from encoding the data and detecting and correcting the errors that might happen in the transmission, or so what is the third thing that can also happen? So just imagine that you have data 1001, whatever, the streams of zeros and ones being transmitted from the sender. Can you think of another very important problem that can arise in the process? Who can tell? It is called the flow. Okay, so flow basically. So there is something called flow control. Flow control means, let me first write it down. Flow control. So flow control means, like, it might so happen that the rate at which the sender sends the bits, it doesn't match the rate at which the receiver basically can handle this kind of the same rate of transmission. It cannot handle. So basically, the sender overwhelms the receiver in terms of the rate of transmission of the bits. So you need to control that, right? So there needs to be some kind of a synchrony in terms of the rates of transmission and the reception. Okay, so this is called flow control. So if we can manage these three things, then more or less we can have successful transmission between one sender and a receiver. So let us try to understand that one by one how to handle these things. So first of all, you need to detect if there is a problem. You need to detect that problem, and then you need to also correct that problem, right? So one by one, let us take up and let us try to understand how you can handle it. So first, let us talk about this encoding, right? So it is called line encoding. So let us talk about line encoding in the context of digital transmission. Is my slide visible now?
Yes,
Is
sir.
it visible? Yeah. Okay. So let us go ahead and try to understand this. Okay. So when we are talking about transmission, right? So this transmission of this kind of data, binary data, so zeros and ones, okay, so across a link connecting two computers, this can be done in either the parallel mode or in the or in the serial mode, either in the parallel mode or in the serial mode. In the parallel mode, basically, you are going to send multiple bits with each clock tick, whereas in the single mode, only one bit is going to be sent at each clock tick. So for parallel transmission, there is no further classification of it. However, for serial transmission, there are three different types of serial transmission that can happen. And this is where we are going to focus mostly in the rest of the chapter. So first, let us have a quick look at how this parallel transmission looks like. So you have a sender, you have a receiver, and you have let us say n number of wires running between the sender and the receiver. If we have n wires running between them, then at any instant of time, you can have n number of bits that can be sent parallelly. Together they can be sent. So if we have 8 wires, we can have at any instant of time 8 bits that can be sent at the same time. Now in serial transmission, this is not the case. We have a sender which has some digital data, and we have a receiver that is supposed to receive all these data. So unlike in the case of parallel transmission, in the serial transmission, bit by bit, the data follows. Okay, so not all of them are going to be sent at the same time. So bit by bit, these sequentially, these data, they follow over the wire. So let us try to understand that how this can be done. One of the ways in which it can be done is basically through asynchronous transmission. So in asynchronous transmission, there is the concept of the start bit and the stop bit. Okay. So between the start and the stop bits, the actual data to be transmitted will be there. So let us say that if this is the direction of the flow of the data, you are going to have chunks of data which will be preceded by a start bit, and then it will end with a stop bit. The start and the stop bits basically are going to determine the end of the data and the beginning of the data, and the end of the data, right? So this is how it looks like in asynchronous transmission. Okay, so you see that there is a start bit and there is a stop bit. Then there is a gap, start bit, data, stop bit, gap, start bit, data, stop bit. So like this, basically, there is gap between the different data units. There is a gap between the different data units. So in other words, every data unit will be preceded by a start bit and will be followed by a stop bit. This is the process in which this asynchronous transmission can take place between the single sender and a receiver connected through some wire. Now, there is another type of transmission. See, the problem with this asynchronous transmission is that you had to use this additional start and the stop bits. While this is easier to demarcate the start and the end of the data units, but actually this is adding more data to the communication channel. So for this, you can take help of another type of transmission, which is called the synchronous transmission, which doesn't use any kind of start bit or a stop bit. So if you are not using the start and the stop bit, the sender basically sends the streams of bits one by one, and it is the receiver which is tasked to group the bits together. The receiver basically will have to group them in the form of something called frames, and these frames basically are going to be identified with a start and the end byte. So there is the frames, every frame will have a start byte and it will have an end byte, and in between these bits will be grouped into different bytes, and these bytes are going to be constituted within a frame. So if you look at every frame, the frame basically has these chunks of bytes which are there, which basically carries this info in data, and then there is this start byte and the end byte, which basically helps to demarcate the boundary of the frame. So this is basically the synchronous transmission. There is another type of transmission which we will not encounter much in this course, which is called the isochronous transmission. So in isochronous transmission, it is said that the gaps between these different frames that you have seen in the case of the synchronous transmission, These gaps cannot be uneven, so they all have to be of equal length. Okay? Equal gaps have to be there between these transmission of these frames. So let us quickly try to get into what we were talking about, this encoding. So we have digital data, it has to be sent as digital signal. So how this digital to digital conversion is going to take place? Okay, digital data in the form of digital signal. So this is what I was talking about earlier. So you have a sender computer, you have a receiver computer. So you need a pair of encoder, decoder in order to encode this digital signal in the form of, digital data in the form of digital signal, which actually is going to be transmitted over the wire, and then it is going to be decoded at the decoder end of the receiver, and this digital data is going to be extracted at this receiver. Okay, so this is what has to be done. So you need to convert a string of ones and zeros into a sequence of signals that denote the ones and zeros. So for example, the 0 could be encoded as minus v, and 1 can be encoded as plus v. So this could be 0, this could be plus v, could be plus v means positive voltage, right? Negative voltage 0, positive voltage 1, negative voltage 0, positive voltage 1, or it could be the other way around also, the way it is encoded basically. Some kind of representation signifying that 0 means minus 5 voltage, 1 means plus 5 voltage, 0 means minus 5 voltage, plus 1 means plus 5 voltage, like that actually is going to be transmitted. So this is one way, right? This is a very naive and primitive way in which this encoding can be done. So I will show you the different ways in which the encoding could be done. But before that, we need to really understand another concept, which is the signal. Okay, so relation between data and signal. So first, let us try to understand what is the relation between the data and the signal. Okay, so you see that what we are trying to do over here, we are trying to encode a bit to a signal element. This is what we are trying to do. We are trying to encode a bit in the form of a signal element. So let us now try to have a look at this particular picture. So you have 1, 0, 1. So here it is shown, it is represented this way, it is encoded this way, that 1 is minus 5 volts or minus V volts, and 0 is plus V volts. Minus 1 is minus V volts, and if there was a 0, that would be plus V volts. So you see that this is one signal element. So in this particular case, in this figure, what do you see? That one data element and one signal element, they are of the same length, right? So in other words, one signal element is used to represent one data element in this particular scheme. One signal element represents one data element. Is this clear? Any confusion? Look at this particular picture. So in this picture, what do you see? One data element corresponds to two signal elements. One data element corresponds to two signal elements. In the third case, we have two data elements, 0, 1 or 1, 1, corresponding to one signal element. And in the fourth case, we have four data elements which are encoded in the form of three signal elements. So there is a R factor which basically gives the ratio between the data element and the signal element. So this R factor is the ratio between the data element and the signal element. So over here, what is R? 1 by 1 equal to 1. In this case, one data element corresponds to two signal elements. So what is R? R equal to 1 by 2. Here, R equal to 2 by, R equal to how much? 2 by 1. 2 by 1. So which is 2. And over here, how much? are equal to 4 by 3. 4 data elements, 3 signal elements. So you can do whatever, whatever representation you feel, you can do it, right? So whatever, but you have to be consistent in terms of the encoding and the decoding. Now, so what is the relationship between this data rate and the signal rate? So we need to understand. So we have understood the relationship between the data and the signal in the form of this R factor. But now let us try to understand the relationship between the data rate and the signal rate. So the data rate basically defines the number of bits that can be sent in every second, bits per second, right? It is also called the bit rate. The data rate is also called the bit rate, bits per second. So in every second, so let us say that if this time duration was 1 second, how many data elements did we send? 3. So 3 bits per second. Okay. The signal rate is the number of signal elements that are sent in a particular second. So while the data rate is measured with the unit bits per second, the signal rate is measured in the form of the unit called baud. So signal rate, number of signal elements per second, is the signal rate, the unit of which is baud. In contrast to the number of bits per second, which is the data rate. And so do you understand the difference between it? So data rate and signal rate are two different things, two different concepts. So you need to really understand. So if you are given a problem where you are given the bit rate, so you know that it is the data rate. But if you are given a problem where you are given the baud rate, you need to understand that it is not the data rate, but it is the signal rate, number of signal elements that are sent in a particular second. Okay. So with this background concept, let us move ahead. So baud rate can be measured with the help of this formula. So this baud rate or the signal rate is represented typically as S. So S equal to C times N times 1 by R. And what is this R? This R is this factor that I was talking about earlier. Here R equal to 1, R equal to 1 by 2, R equal to 2, R equal to 4 by 3. So number of signal elements by number of data elements. Sorry, number of data elements by number of signal elements. It's the other way around. So that is the R, right? So S equal to C times N times 1 by R. So what is C? C is called the case factor. So in the worst case, in the best case, in the average case. So typically, you'll find like, mostly we'll be doing some kind of an average case kind of scenario in which the case factor is typically going to be like 1 by 2 on an average, right? On an average means 1 by 2 case factor. So, the data rate is N. Okay, so N over here is the data rate, and R, as I said, is the ratio between the data element and the signal element. Now, let us do this problem. Very quickly, within a minute, very simple arithmetic. Maybe you can do mentally also, mental arithmetic. Can you work on this particular example? So the problem is that a signal is carrying data in which one data element is encoded as one signal element. So what will be the R value? R equal to 1. So if the bit rate is 100 kbps, what is the average value of the baud rate if C is between 0 and 1? Very quickly, please do this problem, and within a minute, I'm going to get the answers from you. Okay, so everybody has done it. Very simple. What is the answer? What is the answer? Okay, Ravi, what is the answer?
50
You have
kbaud,
got 50,
50
50
kilowatt,
bots, 50
50
kbots. Okay, okay. Anybody else has a different answer? Okay. So I hope that all of you are attentive. Okay. So this is very important. I'm not able to physically see you, but I am assuming that you are in the third year and you all are self-motivated. You are attentive. Okay. So make sure you are doing so. You are right. It is 50 kbaud. Okay. So how do we get? We use the same formula. S equal to C into N into 1 by R, right? So N is given, R is given, so only the C. Now what is the C? C is the case factor, and it is given that on an average, what is the average value of the baud rate? So on an average, what it is going to be if the C value lies between 0 and 1. So on an average, it is assumed that it is going to be 1/2, right? So C equal to 1 by 2. So 1 by 2 into N into 1 by R, which is this. If you do this calculation, you will get 50 kilobauds. Now let us look at another problem. So in a digital transmission, the receiver clock is 0.1% faster than the sender clock. So how many extra bits per second does the receiver receive if the data rate is 1 kbps? And then the question is that how many it is going to receive if the data rate is 1 mbps. So the receiver clock is 0.1% faster than the sender clock. And this is what I was telling you earlier, right? So basically, somehow these clocks will have to be synchronized, right? So it is said that the receiver clock is 0.1% faster than so the receiver can receive faster by the factor 0.1. So there is a so 0.1 is the factor. Okay, so how many extra bits per second does the receiver receive if the data rate is 1 kbps? Who can do it? So let me, in the interest of time, let me show you the solution. Okay, but all of you please try these problems yourselves, and remember that in the exam you will get many problems. Okay, many different types of problems you are going to get. Okay, so make sure that you practice problems. I will also help you to in your practice. So let me just cover this theory part, and then more problems I'm going to run you through. Okay, so maybe I will give you a set of problems to work on, and then then we'll see how to look at your solutions. So at 1 kbps, the receiver will receive how many? 1001 bps instead of 1000 bps. So at 1 kbps, the receiver receives how much? 0.1 faster, 0.1% faster, right? So 0.1% faster than the sender clock. So basically the receiver will receive 1001 bits per second instead of 1000 bits per second. So the sender sends 1000 bits in a second, the receiver is going to receive 1001 bit per second. So one extra bit the receiver is going to receive per second. So at 1 mbps, the receiver will receive this much bps instead of this, right? So which means that this is what is going to be sent at the sender end. The receiver will be receiving this much, and the extra bps that it can receive is 1000 extra. Okay, so now let us get into what I was telling you. So you now have the background, you know what is the bit rate, what is the baud rate. Let us now try to understand that how this digital data can be sent from the sender to the receiver. So for this, you need to do something called encoding, line encoding. So what you have to do? You have to represent every bit with a particular type of signal element. You will have to represent, you will have to encode you will have to name with a certain convention a particular bit and associate that bit with a particular type of signal element. So what are these different possibilities? We'll see. So this kind of thing can be done with many different types. One is called the unipolar mechanism. Each of these I am going to talk about shortly. So unipolar mechanism, in unipolar, the most popular scheme is the NRZ, non-return to zero. Then you have the polar mechanism, polar schemes. There are a couple of different ones. NRZ, non-return to zero, RZ, biphase, and so on. See, NRZ occurs in both, because you can have unipolar NRZ, you can also have bipolar NRZ. Okay. Then you have this bipolar mechanism, in which we have AMI and pseudo ternary. There are a few other mechanisms also for encoding, which in this course it is kept out of the syllabus. So multi-level and multi-transition schemes are also there, but we are not going to cover them here. So let us try to understand this unipolar NRZ. So unipolarity, okay, non-return to zero. Non-return to zero, basically, as you can see over here, plus V voltage will be representing a particular type of bit, and then zero, okay, this 0 bit will be represented as 0 voltage. 1 bit will be represented as plus V voltage. 0 bit will be represented as 0 voltage. 1 bit as plus V voltage. 1 bit as plus V voltage. 0 bit as 0 voltage. Very simple. But this mapping between this bit and the corresponding voltage level is very crucial. Now, this is what basically is done in unipolar mechanisms. So you see, unipolar means there is no different polarity, right? It is only positive voltage, 0 and positive voltage, right? So in unipolar mechanisms, as you can see over here, the signals basically all lie on one side of this axis, only one side, on the positive side. There is no minus V over here. There is no negative voltage. So if you look at the power, what is the average power, normalized power? It is going to be half of V square. How? So power, basically, power is equal to, is measured as what? From your basic physics, power is measured as the product of V and I, voltage and current, right? And what is I? I equal to, if you want to represent in terms of V and R, I equal to V by R. So you can also say that power equal to V square by R. Now, if we are talking about unit resistance, then power becomes what? V square. So what is the power over here, power level over here? V square. What is the power level for 0? It is 0 square. So V square power level is V square. Sorry, V, this plus V power level is V square. 0 V, the power level is 0 square. So what is the average? Half of V square plus 0 square equal to half of V square. This is the normalized power. Is it clear? Now, this scheme is very plain and simple. It can be used, but there are certain problems with this scheme. Okay, there are certain problems with this scheme. So we need to understand this scheme basically suffers from something called baseline wandering and the existence of DC component. So we need to understand what are these two things. There is another metric, there is another factor which is also important to evaluate these encoding mechanisms, which is called synchronization, right? So this scheme has no synchronization or any kind of error detection, but it is simple to implement, but it is costly in terms of power consumption. Okay, so power consumption is what? Average power consumption, normalized power consumption is half of V square. Okay, so it is more costly in terms of power consumption. It's a factor of V square, basically, product of V, right? So now let us try to understand what are these different terms. Baseline wandering. Okay, so please take a note of it. Okay, so what is this baseline wandering? So we need to first understand what is this baseline. Okay, so when you are sending the digital signals, the receiver, it gives a baseline. This baseline is basically the running average of the received signal power. It gives a running average of the received signal power. So what happens is that any further incoming signal will be evaluated against this particular baseline to understand what value it carries in the form of data element. So if a long string of zeros and ones are received at the receiver, then basically there will be a shift from the baseline, obviously, and that will make it difficult for the receiver to decode the bits correctly. So this shift from the baseline, this normal average received power, this running average received power, which is the baseline, the shift from it is actually called baseline wandering. The shift from the average received signal power is called baseline wandering, and this happens when there are a long string of zeros or ones that are received at the receiver. So the problem is that due to baseline wandering, the receiver will have difficulty to decode the data bits correctly once it receives it. So this is baseline wandering. So what is the other concept that we talked about? DC component. So this DC component and baseline wandering are actually related. So I said that it is not desirable to send a long string of zeros and ones, right? So when the voltage level in a digital signal will remain constant for a while, this would indicate that there are a long string of zeros or ones. So long string of zeros means what? It is remaining, let us say, zero voltage for a long duration of time. Long string of ones means it will remain as plus V voltage for a long duration of time. So due to this, basically, the spectrum creates very low frequencies. And this comes from Fourier analysis, which you don't need to think about much deeper, but just remember that the spectrum basically is going to create very low frequencies due to the existence of these constant voltage levels for long durations of time. Okay, so these frequencies basically, they center around the zero frequency, and these are called the DC component, the direct current component. DC means it is coming from your voltage, I mean this electrical circuits, basically direct current components. So these DC component, existence of DC component is not very desirable. Okay, and it's going to pose problems for systems that cannot pass low frequencies through it. Okay, so that's the DC component. Let us also, not required over here, but let us also quickly try to understand another thing that is required, which is called self-synchronization. Okay, so when the signals are received from the sender, the receiver's bit intervals must also match exactly the sender's bit intervals. Now, if the receiver clock is faster or it is slower, as in the problem that I was showing you a while back, these bit intervals are not going to match at the sender and the receiver. So this will lead to the receiver misinterpreting the signals that are sent from the sender due to this mismatch in the clocks. Okay. Now, so this kind of thing is not desirable. So you need to have some kind of synchronization. So self-synchronization, okay, has to be enforced, right? So a digital signal basically has to be self-synchronizing. That basically should include the timing information along with the data that is sent. Okay. So this can be done in different ways. One of the very commonest ways to do it is to use transitions in the signal. Okay, use transitions in the signal. So whenever there is a transition, that alerts the receiver that it is the beginning of the pulse, middle of the pulse, or end of the pulse, right? So basically, if there are transitions in the signal, that alerts the receiver to the beginning of the pulse, middle of the pulse, or end of the pulse. And if the receiver's clock is out of synchronization, these points can reset the clock. Okay, so these are the three different things that we'll encounter in the rest of the encoding schemes as well. So this is the unipolar inner Z. Like this, there are few other schemes. So unipolar inner Z basically suffers from baseline wandering and existence of DC component. And let us now look at how these problems can be addressed. Let us quickly have a look at another one, which is the same inner Z, non-return to zero, but polar inner Z. Okay. So this can be classified into two types. There are two versions of it. One is called the inner ZL, and the other one is called the inner ZI. Inner ZL corresponds to non-return to zero level, and the inner ZI basically corresponds to non-return to zero inversion. So as you can see that in unipolar inner Z, it was only plus V voltage or 0 volt for encoding the 1 and the 0 bits. Here we have the voltages on both sides of the time axis. So we have plus V volt to represent 0, minus V volts to represent 1, plus V volts to represent 0, minus V volts to represent 1. So earlier it was what? It was 0 voltage to represent 1. So now we have minus V volts to represent 1. So you see that this basically can help you to balance the polarity of the signal, right? So inner ZL, okay, and then we have inner ZI, where the change or lack of change in polarity is going to determine the value of the symbol. So the symbol 1, the bit 1, will invert the polarity, and the symbol 0 is not going to do so, or vice versa, right? So in this case, we are using the symbol 1 to invert polarity. So 0 plus V volt. When 1 is encountered, the polarity is inverted like this. 0 is encountered, no inversion of polarity. Again 0 is encountered, no inversion of polarity. 1 is encountered, so inversion of polarity. Again 1 is encountered, inversion of polarity. Again 1 is encountered, inversion of polarity. 0 is encountered, no inversion of polarity. So this is how the inner ZI scheme works. So you can see over here, if you look at this particular plot, so plot of P, that means the power versus the frequency. So as you can see over here, at lower frequencies, more power gets consumed. Okay. But at higher frequencies, basically, this power basically reduces, power consumption reduces. Okay. So this is basically how this polar inner Z works. There is another polar scheme which is called the return to zero, where there are three voltage levels that are used: plus, 0, and minus, plus V, 0, and minus V. So here actually, unlike in the previous schemes where the transitions were not landing into a zero, here in polar RZ schemes, the transitions will first go to zero and then it will change to either plus V or minus V. So this is how it looks like. So you see that, when a zero is encountered, it lands to zero, minus V to zero. One is encountered, okay, one is encountered, plus V to zero. Again, zero is encountered, minus V to zero. Zero is encountered, minus V to zero. One is encountered, plus V to zero. So this particular scheme is good in terms of balancing the DC component or taking care of the issue of baseline wandering. Okay, and this is also good in terms of self-synchronization. Okay, this is also good in terms of self-synchronization. So if you think a little deeper, you will be able to make out why it is so. Okay, so this return to zero is good in terms of solving the problems of DC component, baseline wandering, and self-synchronization. So now we do not have time, but let me very quickly show you two other schemes, which is called the polar biphase Manchester and differential Manchester. So you see, we have in Manchester and differential Manchester, we have mid-bit transition. We have mid-bit. So this is the bit interval. So within the bit interval, there is a transition. This is called mid-bit transition. So here in Manchester, 0 is represented with the help of this transition in the bit interval, whereas 1 is represented this way. So 0 is this transition, 1 is this transition. 0 is this transition, high to low. 1 is, again there is 0, so high to low, and 1 is low to high. 1 is low to high, so on. So this is how this this scheme basically works. Okay, is it clear? Okay, and then you have the differential Manchester, where every symbol has a level transition in the middle, but the level at the beginning of the symbol is determined by the symbol value, and one symbol causes a level change that does not. So let us try to understand this, whatever I just read out. So if you have no inversion, that implies that the next bit is 1. If the next bit is 0, you need to invert. So next bit is 0, invert. Next bit is 1, no inversion. Next bit is 0, inversion. Next bit is 0, inversion. Next bit is 1, no inversion. Next bit is 1, no inversion. Is it clear? Okay. And one last thing is this one, then we'll stop for today, which is the bipolar AMI and pseudo ternary. So this particular scheme, it uses three voltage levels: minus, plus, 0, minus. So here there is a typo actually. So we'll understand this, how it works. So the voltage level for one symbol is going to be at 0, and the voltage levels for the other basically alternates between plus and minus, plus and minus. Okay. So AMI basically refers to alternate mark inversion, bipolar alternate mark inversion. So the 0 symbol is going to be represented by 0 voltage, and one symbol will alternate between plus V and minus V. So let us try to look at this particular scheme. 0, 0 voltage, 1 plus V. 0, 0 voltage, 1 will invert, it will become minus V now. Because the previous one was plus V, this one, the next one is going to be minus V. And the process continues. Is it clear, AMI, how it works? And one last thing is the pseudo ternary. In pseudo ternary, you have exactly the same thing like AMI, but the polarity is reversed. So 0 was 0 voltage over here. Here 0 is plus V voltage. And then for one it is 0 voltage. Then the next 0 comes. The previous 0 was plus V voltage. This 0 will become minus V voltage. Again 0 comes, because this was minus V, this will become plus V. 1 comes, no change, 0 voltage. And because the previous 0 was plus V voltage, this 0 is going to be minus V. So what I want you to do now is that before the next class, all of you will have to come prepared to have a table of comparison between all these schemes that I covered with respect to 3 factors. Number 1, DC component. Number 2, baseline wandering. And number 3 is the self-synchronization. With respect to these 3 particularly, and if there is any other point of difference that also you can find out, that is fine. I want you to come up with a tabular table of comparison comparing these 3 these different encoding schemes. Okay, it is very important. This is a homework for you. So all of you please come prepared. In the next class, I'm going to randomly check with the students who has done what. Okay, so we are little over time, but I hope that you got a lot of knowledge today, and there are a couple of other things also that has to be covered in terms of block encoding, block coding, and scrambling. So those things I will cover next class. So for today, this should be enough for you. So thank you, and so please, whatever has been covered, please make sure that you come prepared. You read them yourselves before the next class. Okay. Any question, anybody?